new video, right? بسم الله الرحمن الرحيم. قالوا سبحانك لا علم لنا إلا ما علمتنا إنك أنت العليم الحكيم. Please don't bring this device in the exam, okay? So you don't lose it, or you might get a not good situation. So today, inshallah, we're going to cover the new section about antenna radiation characteristics. When you are designing an antenna like this, when the customer comes to you asking you to design an antenna, what are the parameters you should look at? What are the design specifications? Like when you design a car, you need to know what is the maximum speed, engine, RPM. You need to have some specifications. These are the antenna characteristics that we should take care of when designing an antenna. We have the total radiated power, antenna pattern, beam dimension, antenna directivity, radiation efficiency, and gain, antenna radiation, and loss resistance. These are 6 characteristics of any antenna that we should understand and be able to achieve the design objective regarding this stuff. Why pi equal to 3.15? 3.14. Why? What are this value? No idea? Please write your name in the sheet. I will come to your class. Okay, who said that pi equal to 3.14? Maybe it's a lie. So what is the meaning of radian? What is the meaning of 1 radian? If you have an angle of 1 radian, what does this mean? It is the angle subtended faced by an arc of length r. R is the radius of the circle. So if you take an arc of the same radius, this is 1 radian. Agree? So this is the definition of radian. 1 radian is the angle subtended by 1 r. If you take some angle here, such that the arc faced by the angle or subtended by angle is r, same as the radius is r. So this 1 radian. What about if I take one more r? Okay, then another r. Then another little bit more r. So I will take 1, 2, 3, and this guy 0.14. So how many r I have here? How many r I have? 3.14 r, right? This would be something like this. Would be 183. So if I need to take here, if this number becomes 3.14 r, what should be the angle here? What should be the angle I have? I choose this value because this value will make r cover half the circle. This value will be the same value here. Look at the same value here. Just take the cross. If you have 1, you will have 1. If you have x, you will have x. So 3.14 r is 3.14 radian. What's the call pi? They call it pi for sure. So this is the story of pi. Okay? This is half the circle measured in radian. So you will go r. What about if we need to take the whole thing? Do you guess how many r we will have to cover the whole circle? 6.2. 1, 2, 3, 4, 5, 6, and small piece. 6.2. So 6.2 r. How many radian covered by 6.2 r? 1, 2, 3, 6.2. How many radian should I have? 6.2. What's 6.2? 2 pi. This is the story of pi. Why people like to use r in some situation? Why people like to use r rather than degree? So can you think all the time? Why sometimes we use the radian? Search for it. I think for simplicity, because 360 degree is big angle. So when you try to add or repeat this, you will get up with big numbers. But 4 pi or 3 pi, 2 pi would be manageable in mathematics. It's easier in mathematics, I think. That's it. So now we come to a new angle. This is 2-dimensional angle. The radian is 2-dimensional angle. There's another kind of angle, 3D angle, 3-dimensional angle. We call it radian. So this is a sphere, not a circle, a sphere. If you take a part of this sphere, such that the area faced by this part equal to r squared, the spherical area on the sphere. If you take this area to be r squared, this angle will be 1 steradian. This, it will be look like what? This angle. Something like this. Kurtos. This is 1 steradian. So assuming we have a spherical sphere here. And this is part of the sphere, where this area is r square. What's the radius of the sphere? If this area is r square, this angle you see is 1 steradian. It's an angle, a 3D angle. Okay, this is the angle you have. Such that the area phased is r square. R is the radius of the sphere. Clear? So, having said this, so 1 steradian is phased by 1 r square, right? One solid angle. Solid angle is defined by this symbol. This symbol means solid angle. So 1 steradian of solid angle phased by r square. How many steradian ya Ryan phased by 16.5 r square? Ryan. So this will be 1. So what should I write here? Yes, cross product, right. What's the problem? So what should I write here? Huh? So 1 steradian phased by 1 r square. How many steradian phased by 16.5 r square? The same number, 16.5. Right? Should write here 16.5. Are you following me, Shabab?
Yes.
What should I write here at the end? Is the same value, 16.5. So 16.5, 1 steradian, or one of this guy, phased by r square, is called 1 steradian. How many steradian phased by 16.5? Why I choose this now? What's the name of this? What is 16.5? 2 by? 3 by? 4 by. 4 by is 60.5. 60.56. So 4 by r square will be phased by how much angle? 4 by steradian. You know if you add this area, if you cover 16.5, it will be the whole sphere. Okay? The spherical area of the sphere. It's a 4 by r square. 4 by r square is equivalent to 4 by steradian. Did you get this? Again, quickly. So the definition of steradian angle is the angle phased up by an area equal to a r square. Not too late. What is that in this sheet? So if this angle, again, this angle is phased by r square. So 1 steradian is phased by 1 r square area. How many steradian? If I need to cover the whole sphere, how many r square I will need? 60.5. 4 by r square. And if you need this area, 60.5, it will give you the whole thing. So what should I write here? 1 gives 1, 60.5, which is 4 by. So 4 by steradian, the whole angle here will be covered by 4 by r square. Agree? Based on what I have said, if I give you some unknown angle in steradian, so if I give you a bigger angle covered by a bigger area, so if I give you bigger angle covered by some area, what should be the angle in steradian here?
90.
No, I give you random, any area. I take an area of the sphere. What is the solid angle phased by this area? Okay, yeah, this is r square. If I take another one, and another small piece, it will be an area. What is the new angle? So again, 1 steradian is 1 r square. 4 by steradian, the whole sphere is 4 by r square, right? If I need to have here some unknown steradian, and I have the area is given, what should be the number here?
The symbol is area.
The area of r square. You take this over r square, give you this number. So the angle in steradian is the area phased over r square. This is what we have here. Are you getting this? The unknown angle, the unknown of this angle, is the area phased, this area, over r square. Because this is what I do here. 4 by means 4 by r square over r square. Okay, Shabab? So this is what I need you to know. What I need you to know today is that this formula, look at this formula. If you have some unknown angle here, and I give you the area could be r square or whatever. This angle is measured as the area phased over r square. Very simple. By definition. Make sense? Why you look impressed?
صارت واضحة أكثر.
ها؟
صح، هذه الصورة أوضح من اللي قبل.
Okay, so one steradian is faced by r square. X steradian, x of this angle, faced by x of r square. So whatever angle unknown, you need to find the area over r square will give you this angle. Does this make sense? This is the formula we use in this part. So, because now we need to find the radiated power from an antenna. Assuming we have very small area over the sphere, very small area. This area will be equal to what? If you take very small area, it is equal to r squared sine theta d theta d phi. Agree? What is the angle? What is the solid angle of this area? Like this. Look, this is here. The angle, the area we have here is this guy by definition. So how big is the angle down here? The solid angle.
The area over r
The
square.
area over r square. So this is the solid angle. This guy over r square. So d omega means differential solid angle. This small solid angle faced by this area is the area over r square. So whatever you have here is the solid angle. Agree? Again. So I have a sphere. I have taken very small area. This small area is defined by r squared sine theta d theta d phi. What is the solid angle of this small area? What should be the solid angle? And I know the area equal to this. So the solid angle d omega will be this guy over r squared. The whole thing over r squared. So the answer will be this guy, which is d omega. That's it. Easy? Huh? This by definition, we know this from high school, from physics, when you took spherical coordinates. So the differential, what I need you to know is that the small angle, the small solid angle here is defined by dA over r squared. The same formula we have here. The same formula here. The solid angle is the area, whatever you have here, over r squared. So I did the same. The solid angle is this area over r squared, which will be sine theta d phi. The whole solid, if you need to find the whole solid angle here of the circle, the whole thing here, it will be the spherical area of the sphere, 4 by r squared over r squared, it will be 4 pi. Very easy, very easy. Now, what is the radiated power? The radiated power is average power density times it. Agree? The radiated power in watt is the average power density, watt per square meter times L. This small area. The small area, what is the direction of this small area? This is vector and vector, dot product. The area has what direction? Look at the area. This area. What is the unit vector normal on the area? What's the unit vector here? R. So the area has direction of R. D has direction of R. And S, what is the direction of S? S is a vector. Phi. What's the direction of S? It was E cross H. And E in theta, H in phi. What was the direction? R also. This guy has R. So R will cancel. So the average power, the radiated power in watt is average power density times the area. That's it. Scalar. What is dA? What is the small area we have here? This guy. R squared times this is phi. You must review the spherical coordinates as I told you last time. So how you will substitute the area. Now the total radiated power. What is the total radiated power? It is the integration of dBA. dBA is just root. So it is average power density as a magnitude times delta area. Delta area is this guy r squared times theta d phi. Are you following? And what I have here, all of this part يا شباب. Look at this part. Look at this part. Times this. This is delta area. Delta area is r squared times all of this. So the integration of the whole sphere of S times this guy will give you the radiated power. I can substitute S by F over S maximum. Because the definition of the normalized radiation intensity is S over S maximum. So I can replace S by F, as we did before. F is S over S maximum. So at the end of the day, this formula is what we need. The total radiated power from this antenna, or from any antenna, the total radiated power equal to the integration of the normalized radiation intensity, R squared, and the maximum of the average power density. So you must have this guy, you must have S. What is S? 1 over 2 real part E cross H conjugate. You must find S. Then take the maximum of the S, it will be this value. What is F? What's the value of F? S over S maximum, which has maximum of 1. This guy. So by finding F and S maximum, you can find the total radiated bulk of the antenna. Okay, Shabab, very easy, just read it with open heart. This is the definition of the radiation pattern. This is the radiation pattern of your dish antenna. You know the dish in your house, it's directive. It's not like this antenna. This antenna is only directional, that has equal radiation in one plane. But the antenna in your house, the dish antenna has this directive radiation pattern. It gives much power gain, much higher gain. Like this antenna, this is like the dish in your house. The radiation pattern of this antenna is this guy. So the antenna should be placed here to give you maximum radiation in this direction. Down, below the antenna, there is no radiation. All the radiation goes here. Okay, Shabab? It's a much higher gain antenna. This is 3D pattern. As I told you, this 3D pattern. Look at the 3D pattern. It has one main loop, this one main loop, and it has some side loops. This is called side loops. I think I covered this. There are two ways to sketch a radiation pattern. As we have done, we have used the polar coordinates. Polar coordinates means the angle theta or phi is changing over a circle. Called polar, this polar, could be. So you have here theta is 0, 90 degree. Look at the angle theta. You have rectangular plot, xy. So the angle theta is expanded over x-axis. The angle theta here, ya shabab, 0, 10, 90 up to whatever, over x-axis. Same line. But here, theta is 0, then 10 degree, 20 degree, and so on. Go all around. This is called the polar drawing. This is rectangular drawing. Okay? Very easy, and you can draw the radiation pattern in polar or rectangular coordinates. This one example of radiation pattern in polar coordinates. So the antenna is assumed to be here, this antenna. Okay, and this is the radiation pattern. So if the antenna is here, the maximum radiation is along this direction. If you go down, you have little radiation. Look at the level here, much lower than this. So the antenna is radiating maximum radiation along this direction. Yes, Allah.
دكتور هذا اللي قبل شوي نقدر نقول انه small representation of Smith chart ولا؟
Somehow it has similar to Swiss chart in the polar in taking angle around. It has some similar. So this is the radiation pattern in the rectangular plot. Rectangular plot means I'm drawing here F. I'm drawing F in dB. What is the maximum value of F? F is S over S maximum. Maximum is 1. In dB, what is the value of 1 in dB? 0 dB. So the maximum is 0 dB. The half power 50% on F is 0.5 to minus 3 dB. So here I have X, Y axis F in dB. So maximum is 0. Maximum is 0 means F here has 0 dB. When we go to minus 3 dB, this is a minus 3 dB point. When you go to minus 3 dB, the angle, as I told you, this angle down here, will define the half power beam width. So the half power beam width is النطاق الإشعاعي where the power is above 50% of the maximum power. What do you get this? يعني radiated power above 50%, only in this range. It's not a beam, look, it's a nice beam. The beam is sharp. يعني the half power beam width now, what should be the half power beam width here يا شباب? Look here at this angle. Look at this value. Theta 1 and theta 2 are the angle where the power is 50%. This maximum power is 50%. So it dropped very quickly. What should be this angle? What should be the difference between theta 2 and theta 1?
60.
It's about 5 minus 5, about 10 degree. This 10 degree half power beam width. As if this antenna is radiating maximum power here, then at 5 degree the power dropped to 0.5. Okay, so it's a very sharp beam. Not like if you have maximum radiation here, then the power dropped to 50% here. It has wider coverage. So it's based on application. If you need to cover big area, like the antenna we have in the base station for this mobile phone, to cover big area. So we use like a bigger beam width. This angle will be big if you need to cover big area with the radiation. If you need to have sharp radiation, so I need to communicate with Badr without Muhammad listening to us. I need to send the information only to Badr. So I will focus the beam to be only along this direction. So the other guys left and right will not receive any information. Okay, شباب? So it's based on your application. As I said, in military application, because of security and they need to send the information to the target person, so they try to use high gain antenna or high radiation pattern. So the radiation pattern will be very sharp. It will go only to someone and all the other guys cannot receive it. This is a beam dimension. We have also another beam width called the null beam width. Look at this radiation pattern is maximum. Then it will drop to 50%, then it will drop to 0. This is almost 0. And this point is very little. So this point here is called null, no radiation. Look at this point here. Yes, it will drop lower, but this point compared with this point is like 0. So what we have here, this beam width is the null beam width. So we have null beam width. It is the range of direction where the beam width is within 0 to up to maximum. Okay? Again, it's a measure of how sharp is the pattern. If the pattern drop to 0 along a very small angle, so it is sharp beam. Compare this beam with a beam like this, drop to 0 like this. Look at the bigger beam, at the red one. It will have bigger coverage, but lower, and the 50% is here. Look at the 50%. 50% is big, and the beam width of the null is big. The 0 will be big, and the beam width of the null will be big as well. We have another definition called the beam solid angle. What's the meaning of beam solid angle? Look here at this two radiation pattern. This radiation pattern has maximum radiation. It has some side loops. There's some radiation here. Okay? I will cancel all this. I will cancel all this radiation, and I will assume that I have only one big beam. As if I take this radiation and put it inside. Okay? Now, the radiation pattern will become like a cone. Like this, exactly like this. The cone contains all the radiation. And the maximum of the cone is always 1. The point here has the same level. Not like here. Look here it drop. But here will be like part of the sphere. Sphere, same radius. So I'm replacing the actual pattern by a uniform cone pattern. This angle is the beam solid angle. So the definition of the beam solid angle, of this angle, it is the angle of a uniform cone with the maximum radiation at any point is the same. This angle is called beam solid angle that represents this angle. Okay, again, I have here some radiation. I will cancel all of this, or I will take it inside. Now the new beam will be something like this, a new radiation. So it is uniform. Everywhere you have the same radiation, like part of a sphere. This angle now is called beam solid angle. It's equivalent representation of the antenna radiation. So the definition of the beam solid angle in this case, the beam solid angle is omega b. This symbol omega b is equal to the integration of f d omega. D omega is the elementary solid angle. You remember the omega? The omega here equal to sine theta d theta d phi. The small solid angle. So the integration of f d omega will give you this angle. This angle now equal to this. Okay, so I am converting the actual radiation to a uniform radiation. Then I need to find this angle of the new radiation pattern will be given by this equation. Okay, Shabab? Are you getting what I said? Thank you. You can stop this.